So I'd like to finish up the example that we kind of rushed through at the end of the last lecture. I'll start at the beginning of the example, but move quickly through the first 4 or 5 slides that we kind of covered in pretty good detail, and then take a little extra time on the very last slide or two where we actually did the calculations a little quickly. So our example is a battery in a circuit with 2 capacitors, but with a switch that only allows the battery to be connected to the first capacitor, or when the switch is thrown, for the battery to be disconnected and the capacitors to be connected in parallel to each other. All right, so initially we connect a 9-volt battery up to the 4 microfarad C1 and let that battery charge up that capacitor. And then at some later time, we flip the switch from the left position to the right position, thereby disconnecting the battery and allowing C1 and C2 to be now connected in parallel with charge already deposited on C1. All right, so the question is calculate the total energy stored in the 2 capacitors in the final state. So we just emphasized previously that the circuit consists initially of just a voltage source, this battery, and a single capacitor with the second capacitor out of the circuit. And then once the switch is thrown, the voltage source, the battery, is out of the circuit, and the circuit consists entirely of 2 capacitors that are connected in parallel. Okay, so this part is out of the circuit in the first configuration, and this part is out of the circuit in the second configuration because it's not fully connected, right? All right, so we effectively have 2 simple circuits, the initial state like this, the final state like that. Trying to find the total energy stored in the capacitor, and the only really relevant equation here is that the stored energy is, and you have your pick, right? These are all related by Q is equal to CV, 1/2 Q delta V, or by plugging in that Q is equal to CV, you get 1/2 C delta V squared, or equivalently Q squared over 2C. Now, because, well, let's leave that there for now. We already know that the capacitance of each capacitor, so we need to know the voltage across each capacitor in the final state in order, or we could figure out the charge stored on each capacitor in the final state, and then we can use one of these equations to calculate the total stored energy in that final state. Now that we know what we're going after, let's focus on the first part of the problem. Let's look at the circuit in the initial state and see what we know about it. We've got 9 volts connected across a 4 microfarad capacitor. So we simply, we'll write this out as V0 being across C1. The reason for doing that instead of just labeling it as V1 is that this capacitor will later be in the circuit of the second stage, and it's going to have potentially a different voltage. So I'm not going to label this C1, the voltage across C1 initially as V1. I'm going to rather say it's V0. So then we can calculate the amount of charge that the battery puts on C1. Right? Q is equal to VC. So we get Q0 is equal to V0 C1. And plugging in our numbers, that gives us that the initial charge on the first capacitor is 36 microcoulombs, right? 9 times 4 microfarads. Now, we've fully characterized the initial state, so let's flip the switch and think about what's conserved between the first state and the second state. We know that total charge is conserved, right? Because there's a certain amount of charge now sitting on these plates. When we suddenly flip the switch over to this side, right, that charge is still there at the moment that we flip the switch. And we know charge doesn't just disappear or appear out of thin air. So the total amount of charge between these 2 plates in the final state has to be the total amount of charge that was on C1 in the beginning, right? So initially there was a charge of plus Q0 on the upper plate of C1 and an excess charge of minus Q0 on the lower plate of C2. That Q0 is now spread over the upper plates of both C1 and C2, so that means Q1 plus Q2 in the final state have to equal Q0 in the initial state. All right, so the equations that we've agreed on so far, Q0 is just V0 times C1, and Q1 plus Q2 in the final state have to equal Q naught in the initial state. All right, so that's what we start with. We also know one other constraint. In the final state, you notice that C1 and C2 are just connected in parallel. The upper plates of C1 and C2 are connected with a simple wire, and the lower plates of capacitors C1 and C2 are connected by a simple wire. Right, so they are truly in parallel, which we've determined previously means that the voltage across C1 and the voltage across C2 must be identical. And so for simplicity, we're going to say, let's label that as delta VF. Right? It's delta V1 is equal to delta V2, and to give it a common name, we'll call it delta V final. All right, so let's see what we can do with these equations. We can take the equation Q1 plus Q2 is equal to Q naught, and we can apply Q equal to VC to each one of these terms so that we get Q1 meaning is equal to V1C1, Q2 is equal to V2C2, Q3 is equal to Q naught is equal to V naught times C1, because you remember Q naught was only on capacitor 1. Okay? Then we can combine our voltage definition of final voltage with this equation that we've just developed to write it in terms of VF. Right? So we'll take V1 and just write it as VF. We'll take V2 and write it as VF, and everything else stays the same. But now, looking at this equation, we see that we can effectively just pull the VF out front. So we now have delta VF times C1 plus C2 is equal to V naught C1. So then, doing a little algebra to solve for the delta VF, we can say that delta VF is equal to V naught C1 divided by C1 C2, bringing the C1 C2 over to the other side, and plugging in numbers, we get 36 microcoulombs. That's our V naught C1 is Q naught, divided by the C1 plus C2 is 4 microfarads plus 8 microfarads gives us 12 microfarads, and 36 microcoulombs divided by 12 microfarads gives us 3 volts. So the voltage across each of these capacitors ends up being 3 volts after the switch is flipped to the right-hand side. So finally, we can calculate the energy stored in each capacitor. We pick the appropriate form of our capacitor energy equation, since we know the capacitance of each capacitor, and we just calculated the final voltage across it. We'll choose the 1/2 C delta V squared form, and that gives us, for capacitor 1, 1/2 times 4 times 3 volts squared gives us 18 microjoules, and for capacitor 2, 1/2 times 8 microfarads times 3 volts squared gives us 36 microjoules. So finally, the total energy stored amongst the two capacitors is 18 plus 36, or 54 microjoules total. All right, and that finishes up that example. What I'd like to do now is to finish up the topics in chapter 20 with a few slides that we didn't quite get to at the end of the last lecture, and that has to do with the use of dielectrics within capacitors. So this will help you answer a few homework questions as well. So the formula that we derived earlier for a parallel plate capacitor assumed that there was empty space between the plates, right? Vacuum or at least air. In this case, the equation for the parallel plate capacitor capacitance was epsilon, the permittivity of free space, right? That's just a number, times the area divided by the distance between the plates, right? Where the area is the area of either one of those two square plates or rectangular plates. We can increase the capacitance of a capacitor. Well, we saw before that we can increase it by reducing the distance between them, increasing the area of the plates. But there's a third way that we can increase the capacitance of the capacitor, and that's by inserting a insulating dielectric material between the plates, right? The equation for a parallel plate capacitor that has a dielectric stuck in the middle is now capacitance is equal to kappa times epsilon naught A over D, where kappa is this unitless variable called the dielectric constant. And that dielectric constant, kappa, characterizes a particular insulating material. The value for kappa for the dielectric constant is actually determined experimentally as simply what is the capacitance of a dielectric filled parallel plate capacitor compared to what would it be if the exact same configuration were vacuum filled, right? So something that increases the uh, capacitance of a particular configuration of parallel plate capacitor by a factor of 7 would have a dielectric constant of 7, such as the case of glass. The only ones you're expected to know is that a vacuum is kappa of 1, which means that this reduces back to our original equation, and that the dielectric constant of air is very, very close to 1. It's 1.0006. In this class, unless there's a particular problem that specifically tells you to account for the difference between air and vacuum, we are going to treat the dielectric constant of air to be approximately equal to 1 and treat vacuum-filled and air-filled dielectric capacitors as behaving the same. So we had talked previously about this technology of electroporation, specifically about reversible electroporation, where positive charges in an electric field are being forced to push on one side of a cell membrane, while negative charges moving the opposite direction press on the other side of the membrane, and that pressure causes the membrane to buckle and a pore opens up. If we increase the electric field by another order of magnitude, right, make it 10 kilovolts instead of 1 kilovolt, then you can get to a situation where the electric field is so strong that it actually literally rips electrons off of atoms and molecules. And as soon as that electron gets ripped off, say, in this membrane, it's now a free electron, and then it can accelerate. And that acceleration can cause a cascade of it bumping into another electron and forcing another one off. And very quickly, you end up with what's effectively an electric current running through what should have been an insulating material, because now you have free charges. And so you basically create a little lightning strike inside the membrane. And that is called irreversible electroporation. It's really a miniature version of what happens in a lightning storm, where the charge buildup in a thunderstorm cloud has so much charge on it that the electric field that forms between the cloud and the earth exceeds the maximum sustainable electric field in air. Right? Air is a material as well, and air molecules can have electrons ripped off of it. And so air has what's called a maximum dielectric strength. That's the maximum electric field that the material can maintain before it breaks down and becomes conducting. Right? And so in this case, we have the electric field that's applied to the cell exceeding the dielectric strength of this membrane, and it becomes conducting, and you get lightning strike across the membrane, and that damages the membrane and creates a permanent pore to open. And that's called irreversible electroporation. So I'll show here a table of the dielectric strengths of various materials. This should not be confused with the similarly termed dielectric constant. A dielectric constant, kappa, described how much more capacitance a capacitor will have if you place that material inside the capacitor. The dielectric strength is telling you how large of an electric field you can put across that material before it breaks down and a current starts to run through it. An interesting note is that for cell membrane, studies have shown that the dielectric strength is on the order of 100 megavolts per meter. That's the you notice that this is in the units of an electric field, right? Volts per meter. So this is the maximum electric field that can be placed across, in this case, a cell membrane before that cell membrane will break down and start to conduct. So an interesting calculation to do would be to take this 100 megavolts per meter, right, 10 to the 8 volts per meter, and see what that corresponds to when you look at it across a 10 nanometer thick cellular membrane. Well, 10 to the 8 volts per meter times 10 nanometers, which is 10 to the minus 8 meters, gives you 1 volt, or 1,000 millivolts. The typical resting potential across a cellular membrane for a neuron or say like a cardiac cell, is on the order of 70 to 140 millivolts. So that means the electric field at the cellular membranes of many cells is regularly within a factor of 7 to 10 of the dielectric breakdown threshold. That's pretty impressive, right? A factor of 10 more ions on either side of the membrane would in fact cause a lightning bolt to form in your cellular membranes. So that's an interesting little tidbit.